Okay, so now that we've seen the definition of a linear transformation, we're going to try to see what we're going to do with them now. We'll start by reminding ourselves the first couple examples we had. We had a function that took in numbers and spit out numbers, R1 here, and this function was just fx is 5x. Nothing amazing about that. Our second one took in xy vectors in R2 and spat out a number in R1. And that was f of xy is 2x minus y. However, I can give you some more here without trying to prove them. We can go, say, input three-dimensional vectors and output a number. So f of x, y, z is, let's say, x plus y plus z. All right, that's a perfectly good linear transformation. We can also get things more interesting, say from R2 to R3. So that means we're taking in input vectors that are two components, two coordinates, two-dimensional R2, and the output is going to be things in three-dimensional. So for example, f of x, y is x plus y, comma x minus y, comma 2x minus 3y. And so an example of this would be something like you have a force field, right? You learn about fields involving forces and vectors in Calc 3. So the idea here is, you have these, at every single point, you have a vector representing a force, say gravity or whatever at that point. And so this is a function that takes in a point and spits out a vector at that point. So it's a very commonly used function here. But I want to kind of show you something. In each of these cases, we can slightly rewrite it here. So that instead of just writing out a formula of what x and y and z are, what we can do is we can actually turn this into a matrix of coefficients, and if you just multiply that using matrix multiplication times the input vector, then you will get the output vector. And it turns out that this is actually a general fact here. Any linear transformation can be written as this way. F of x vector is some matrix A times the x vector. And so this shows us, again, I'm not proving this, but this shows us that once we learn everything there is to know about matrices, we will know everything there is to know about linear transformations. They go hand in hand. And quite often, we're going to try to study the function using the matrix, or we're going to try to study the matrix using the function. So it's going to be the same concepts. We're going to do the same systems of equations, row operations, all that good stuff from before. Same things here, but now instead, we are going to be using it to answer questions about linear transformation. So it's same procedures, but looking at things from a different point of view, and doing so can really help us understand things. So let me give you the first example of what we can do in this fashion here. So if I have the function f of x, y is x plus y, x minus y, 2x minus 3y, which again can be written as this matrix multiplication here. And I can say, is the vector 1, 2, 3 in the range? Now at this point in time, I want to point out something here. The range, that's something that you may have learned a long time ago. The range is the set of all possible outputs to the function. And to really hit this hard and understand what's talking about it here, if your function here is x squared, and by the way, x squared is definitely not a linear function, But if you look at that and you look at the outputs, so even though the function goes from R to R, and here, this is the codomain, but even that's the case, the image, or the range, which are the same thing, that's only the numbers that are 0 and bigger, because there is no y values with negative, no points with negative y value. So when we're asking this question here about range, I'm asking, is this vector actually reached by our function? And if not, what can we say? And if it is, what can we say about that? So in other words, we want to say is f of x equal to 1, 2, 3 for any vector x? Well, that means that my output, x plus y, x minus y, 2x minus 3y, has to equal this vector 1, 2, 3. That would give us a system of equations. X plus y is 1, x minus y is 2, 2x minus 3y is 3. And as we saw before, we can write this into an augmented matrix and try to solve it. And I do want to point out something here. Really, we could have just gone straight to the augmented matrix. There was really no point in writing all the extra steps out here, but it can be good to understand where things are coming from at least. So when we have this here, we're going to go ahead and do reduced row echelon form on our calculator, and what you should get is the following. And we have pivots here. Now we need to remember though that we only had 2 input variables here, x and y, and that was it. This is an augmented matrix. And so what that means is this last line, it really reads 0x plus 0y equal to 1, or 0 equal to 1. That's a false statement. And so because of that, what does that mean? That means there is no solution. And if there's no solution to this equation, then that means that 1, 2, 3 is not in the range of this function. So that's just our first example of how we're going to use the row reduction and augmented matrix and all that system equation stuff we've learned already to try to answer new questions about functions. Okay, so then we'll take a break and come back to the next example.